Think about an ambulance driving along past you. Its siren seems to change its pitch as the ambulance approaches and then distances itself from you. Think about it this way. If the ambulance is sitting stationary with its siren on, you hear the siren normally, like this. All these sound waves travel to you at the same frequency they were emitted. Now, if the ambulance moves towards you, the center of each consecutive sound wave moves slightly towards you, such that they begin to bunch up and crunch the wavelength. Since the wavelength has been reduced, the frequency must have increased. Remember, the velocity of a wave won't change within a medium, and so decreasing the wavelength causes frequency to increase. Our ears perceive this increase in frequency as an increase in pitch. This phenomenon is known as the Doppler effect. If the ambulance could travel at the speed of sound, all the waves would reach you at the same time, producing a noise sounding something like this. Though we most commonly notice the Doppler effect as it pertains to sound waves, it is characteristic of all types of waves. This is exemplified by light waves coming from space. As an astronomical object travels towards Earth, the wavelength of the light waves it emits is compressed. If we take a look at the electromagnetic spectrum, notice that decreasing visible light's wavelength moves it closer to the blue region of the spectrum. Thus, on Earth, this object will appear to have a bluish tint. Alternatively, an object traveling away from Earth emits light waves whose wavelengths stretch into the red region of the visible spectrum, and so these objects appear redder. The Doppler effect is contingent upon relative motion. See these two birds flying through the air. Sure, they both have a velocity, but do they have velocity relative to one another? To answer this, let's remove the background. Now they appear stationary. They are not moving relative to one another. They were only moving relative to the background. Now let's watch them again, with the background. Do they have relative velocity this time? Well, let's remove the background. See how they continue to separate relative to one another? Now they do have relative velocity. The birds' relative velocities will be the difference between their individual velocities. If this front bird travels at 9 meters per second, and the back bird at 8 meters per second, the difference is 1 meter per second. The front bird flies 1 meter per second faster than the back bird, and the back bird flies 1 meter per second slower than the front bird. But what if they are traveling in opposite directions? Again, suppose this bird is flying rightward at 9 meters per second, and this bird is flying leftward at 8 meters per second. Well, remember that velocity is a vector. That being the case, these two birds can't both have positive velocities, as they are traveling in opposite directions. If we arbitrarily choose the rightward direction as our positive direction, then this bird's velocity remains at 9 meters per second. But by default, the leftward direction becomes negative, meaning that we have to define this bird's velocity as negative 8 meters per second. We can now find relative velocity. For this bird, his velocity minus the velocity of the other bird gives us his relative velocity, 17 meters per second. For the other bird, the calculation comes out to negative 17 meters per second. So the two birds approach each other with a speed of 17 meters per second as they travel in opposite directions. Suppose they pass one another and continue to move in opposite directions. The fact that they passed each other doesn't change anything. Their velocities are still the same, and so their relative velocities are still the same as well. In the next section, we will use these concepts of relative motion to perform Doppler effect calculations.